Welcome to the lecture for topic 4, part 3. This lecture is all about single replacement reactions. Make sure that you've used the packet to describe the patterns and requirements for the specific single replacement reactions listed. You should be able to tell me from looking at just the reactants that you have a single replacement reaction, and you should also be able to know who is replacing who. So remember that if you have a metal doing replacing, it will replace a metal. If you have hydrogen doing the replacing, it would be replacing the metal. If you have, I guess, of hydrogen in water and of hydrogen in acid, so you have to be careful. This is maybe a typo in the way that I wrote this, okay? But then single replacement by a halogen. So you definitely want to make sure that you know who's replacing who. If you didn't make your notes yet, make sure that you do them. Otherwise, you're ready to go. All right, so remember that in a single replacement reaction, you have an element and a compound. Later on, we'll start to do these in solution, and we maybe won't see the whole compound. We'll only see the ions that are dissolved in the compound, or dissolved in the solution. But for right now, they're going to look like they did in first year. So what you have is two options. Either you have a cation, like the metal anion, the metal cation replacing the metal cation, or you have the metal cation replacing the hydrogen cation, or you have the hydrogen cation replacing a metal cation. So either it's whoever the first ion is in the compound gets kicked out by something that would take its place, or you have a halogen replacing a halogen. When we do single replacement reactions, we do not include oxides. So this will help you a lot, because if you have something plus oxygen, it's probably going to be a CH compound, and it will probably be a hydrocarbon combustion, not a single replacement. Okay, so your options here will look like what we have here, where you have a metal kicking the metal out, or whether you have here a halogen kicking the halogen out. Okay, so these are the things that you're looking for. You will not find oxides. You will find your acid, your ionic compounds, your water, and an elemental metal, or you'll have your acid, your ionic compound, and elemental halogen, I mean, okay? So be on the lookout for that. Keep them straight so that you're not calling that combustion a single replacement. All right, so we do at this level definitely spend a lot of time figuring out what might happen, and we will actually do a whole unit on electrochemistry, which is the reason that this activity series works. The activity series given to you in your packet is a short one. When you did this in first year chem, you probably had a longer one, but we definitely want to have an understanding that this is based on the idea of the potential of something to gain or lose electrons. So we'll spend a whole electrochemistry unit talking about reduction potential and how that fits with this activity series. But for what we're doing right here, you will simply be saying if something is more active than something else, then it can kick it out. So you never have to memorize these. This will be something that you'll have another way of knowing it occurs. It might tell you a reaction occurs, or you see this solid forming or something. So you won't have to memorize this. And the activity series for the halogens is also the group on the periodic table, where you have F, Cl, Br, and I. F is most active and I is least active. Remember that someone to the left over here can replace someone to the right, but someone to the right cannot replace the things to the left. All right, so this is how you use that activity series, and these would be your elements that are going to be kicking the element out of the compound. Again, this is a simplistic view, so once we get to electrochem, you'll see a little bit of a difference. All right, so there's several examples here for you where your metal can replace a less active metal in the compound. Your metal can replace the hydrogen in water. So it's really helpful to write water as HOH if it's a reactant in a single replacement reaction. This is really helpful. All right, because then what you can picture is that what's getting kicked out is only this first hydrogen, not both hydrogens. Notice that this sodium kicks out that first hydrogen. That forms this because it's diatomic, but the sodium ends up with OH, which is the second half here. Okay, so that's a really common error, is that you try to kick out both hydrogen and get an oxide. We're not getting oxides here. Or we can have an active metal replacing hydrogen in acids. And we can have a halogen replacing a halogen, so that the halogen is what got kicked out. Okay, so these are your options. And of course, if it's less reactive, then there will be no reaction. So this chlorine would try to kick out the fluorine because the halogen will kick out the halogen. But when you look at your activity series, chlorine is to the left of fluorine and less active, so this is no reaction. Or the zinc is a metal, it would try to kick out the metal. And we look up here, this is zinc and sodium. Zinc and sodium. Zinc is not more reactive than sodium, so this is also no reaction. So that's how you use that. Some hints that you need to be careful of. I'm not going to do a bunch of examples with you. I think you're going to be pretty good at this. So some hints that you need to be careful of would be to balance the ion charges in the compounds. Remember that you have diatomics. Your elemental halogens and hydrogen will be diatomic. So if they're in a compound, they don't have to be, but if they're free from a compound, so like if they're in a compound, you're going to balance the ion charges. But if they're elemental and free on their own after they've been kicked out or before they do the kicking out, then they need to be written as diatomics. That your more reactive will kick out your less reactive that's like it. The cation kicks out the cation, the halogen kicks out the halogen. And if water is a reactant with a metal, think of it as HOH rather than as H2O. Here's something that's important. If water is a reactant with an oxide of a metal or a nonmetal, then you do not have a single replacement reaction. Okay, then it's a synthesis, and you already know those rules. So I'm not going to do a lot of examples here with you. I will come back up here and walk you through how you would decide a few of these, and then I'm going to let you practice from the packet. So let's look at this example right here. Magnesium turnings would be written as Mg. Magnesium is not diatomic. Added to a solution of iron 3 chloride. So this is going to be Fe3 plus and Cl1 minus, which means I need FeCl3. Notice I balanced the ion charges. I'm going to decide, and the magnesium is a metal, so it would kick out the metal. That would be iron. I'm going to look. Magnesium and iron. Magnesium is able to kick iron out. So that means the iron ends up alone. It doesn't matter which one you write first. I often write the one that's alone first, and then I'm going to have magnesium chloride. So from the periodic table, magnesium and chlorine, 2 plus and 1 minus, is going to be MgCl2. After I'm done with that, then I can come back and balance with coefficients, 3 and 2. That means I need 3 magnesium and 2 iron, and that's your process. Okay, so just be super careful. Make a list of questions if you have them, and make sure that you practice carefully using your activity series and making sure that you're paying attention to charges and balancing equations, etc.